Okay, I guess we can get started. So this last lecture on spatially coupled codes, it's kind of like the last lecture yesterday. It's, you know, not just one overarching thing, but a number of smaller things, trying to just illustrate or get a sense of how these codes do in the finite length regime. Because basically what we've talked about so far is asymptotic results. And what we'd really like to know, okay, for practical block lengths, for practical rates, for practical latencies that we'd be interested in actual system, how do these codes, say, stand up compared to block codes, or how do they perform? We know their asymptotic properties are great, but that doesn't necessarily mean that they work just as well in the finite length regime. So we have several ways of looking at that, different ways of looking at it. Now this is kind of another little way of viewing the decoding. So if you think of this box as representing a terminated spatially coupled graph, and if you just do message passing decoding on the entire graph, just thinking of it as a block code, kind of like that little illustration that we had with the wave effect, you have reliable messages. They're more reliable at the end because, again, these lower degree checks at the end means that the check nodes are connected to fewer variable nodes, which means those are lower rate codes. The local code at the ends are lower rates because you have fewer variables connected to a given check node. Lower rate codes are more powerful in terms of error correction capability than higher rate codes. So that's kind of what gets this wave effect started. And then it propagates from the ends, if we think in terms of termination at both ends, like we've discussed previously, towards the center as the iterations proceed. But the fact that this graph is a localized graph, otherwise the connections, in one iteration you can only communicate locally here. If this were just a random block code, a variable node over here in one iteration could send a message to a variable node way at the other end in one iteration. But that can't happen with this convolutional structure, spatially coupled structure. You can only send messages in one step. You can only go one constraint length bits away from a particular variable node. So this has a very definite localized structure. And you can take advantage of that to consider decoding schedules that are more efficient in terms of reducing the overall memory requirements of the decoder and also the latency requirements. Otherwise, if you decode this way, you basically have to receive the entire block, terminated block, before you start decoding. That's a large latency. And you've got to store all the received symbol LLRs, if we're talking about a Gaussian channel, before you start decoding. And you have to keep those stored throughout decoding, okay? But if you use a sliding window decoder, and it's nothing different than what we discussed earlier, it's just a different picture. The idea is you start with updates in a small window that, based on the localized structure, the constraint length, and then once you've updated these nodes a certain number of times, then you'll decode a set of target symbols. This picture looks quite different than the one we showed this morning. The idea is the same. The set of target symbols would be the variable nodes here at the first time unit. And then this window would shift down by one time unit. And then you'd do more iterations and work on the next set of target symbols. So this is what was introduced. Well, we did density evolution like this back in our 2010 paper, and then the UCSD group developed this as an actual decoding method, which we think is the way to decode these codes in most cases. So the window just shifts and you eventually decode the whole thing. Notice one thing I should say. There's no need, when you look at it this way, it's clear that you don't have to have a fixed termination length L. You can just keep doing this as long as you want. And when it operates kind of in a streaming environment, not so much a block by block environment. So you just continue decoding a set of target symbols each time the window shifts. Now what about performance here? Well, let's try to compare with a block code and compare on the basis of equal latency. So the other issue about the window decoder here is that the memory requirements, this is all the decoder at a particular time has to remember. Once a set of target symbols are decoded, it doesn't have to store those in memory anymore. So the memory requirements are much less and the latency is much less. Otherwise, once we get through with the iterations here and shift the window, we start getting decoded bits. We don't have to wait until we receive the entire block. So latency and memory requirements are reduced with this type of decoding schedule. So if we try to, and they're actually the same. The memory and the latency basically are the same. So on the basis of equal latency or equal decoder memory requirements, let's say we looked at the performance of a 3/6 regular LDPC block code based on a Protograph with lifting factor 1,000. And since there's 6 variable nodes per time unit, the total block size would be 6 times the lifting factor, 6,000. We'll look at spatially coupled LDPC codes, first of all with the same lifting factor. Now the latency of spatially coupled codes, we're using the 3/6 regular, but where we just have the 2 variable nodes per time unit with 1 check node. And so there's 2 variable nodes at each time unit times whatever lifting factor we use for spatial coupling times the size of the window that we'd need in order to, and that would be the entire latency. So if we make this comparison on the basis of the same lifting factor, we get this convolutional gain. And this is the kind of comparison that I made earlier. Okay? We get a large convolutional gain. In this case, it's about 0.6 of a dB, but it can be more substantial than that. But the latency is much higher. If we take the W equal 12 case here, and our lifting factor is also 1,000, then we've got a latency of 24,000, whereas this latency was only 6,000. So this gain comes at the cost of increased latency and memory requirements. So the natural question is, what is the comparison when we have equal latency and memory requirements? Well, we can do that. One way we could do it is simply reduce the lifting factor of the spatially coupled code by a factor of 4, from 1,000 down to 250, and keep the window size at 12. Okay. Now, again, the window size has to be, we'll get to this shortly, the window size just has to be big enough that you're not going to hurt your performance. If the window size was too, you could say, well, we could reduce the latency just by reducing the window size. Yeah, but your performance will fall apart. We'll see that in the next slide, actually. So 12 is an adequate window size for this code. So the window size is either 4 or 6 constraint lengths in this example. And typically it has to be a few constraint lengths in order to get good performance. So we still get a gain on an equal latency basis. Only a couple tenths of a dB, but we still get a performance gain. And now we have some parameters that we can play with here. We could also get the same latency by increasing the lifting factor back up to 500, doubling it, but reducing the window size by a factor of 2. That's going to leave the latency the same here. And actually that does a little better. So there are design issues with spatially coupled codes in the finite length regime that we don't really run into in decoding block codes. There's trade-offs between parameters that are unique to spatially coupled codes. It doesn't show up in asymptotic analysis, but it's clear that there's trade-offs between, for example, here, the size of the window and the lifting factor as to what will give you the best performance. So I just noted that here. This was kind of the first comparison. Paper goes back to an ISIT 5 years ago of comparing these codes at finite lengths and an equal latency basis. Now this is kind of a more detailed comparison of the same thing. This is a different kind of graph. Here we're plotting the required signal-to-noise ratio in dB to achieve a bit error rate of 10 to the minus 5. This is all simulation-based. This is not analysis-based. It would be nice to be able to do this type of analysis, so we're making a little bit of progress on that, at least with the erasure channel now. But this work is all, this is Gaussian channel, it's all simulation-based. But it gives us some insight. So the black curve here is for different block code lifting factors. And the latency is 4 times the block code lifting factor in this case. This is a slightly different protograph than the one earlier where we would have had a 6 here. Okay. The black dotted curve, the required signal-to-noise ratio with different lifting factors for a Protograph-based LDPC block code. And you can see it's simply if the block length is too small, you require quite a large signal-to-noise ratio to get to 10 to the minus 5. But as the block length gets larger, your required signal-to-noise ratio gets smaller. And eventually this is going to go to 1.1 dB, which is the threshold of 3/6 regular LDPC block codes if you go to very large block lengths. So how do the spatially coupled codes, different spatially coupled codes with different combinations of parameters, compare with the block code curve? Otherwise, what we would hope is that if we plot similar curves for spatially coupled codes on an equal, for a given latency, the spatially coupled curve will cut below the block code curve. That means at least we're just saying 10 to the minus 5 here. Things could be different at different error rates, but it gives us some sense. But that we would require less signal-to-noise ratio to achieve that performance with a spatially coupled code than with a block code. So the first curve here is a spatially coupled code with a lifting factor of 160, and we vary the window sizes to see what the performance is. And you can see for really short window sizes, the performance is terrible. Okay, but once the window size gets large enough, then we start getting good performance. So generally speaking, well, it depends on the particular protograph design, but for this kind of the protograph that we used here, we need beyond about a window size of 10. You're not going to do any better. So we just repeat these with different lifting factors, again increasing the latency each time by increasing the window size of the decoder. And we see that indeed these curves all cross the block code curve, and at least for the larger latencies will give us several tenths of a dB gain compared with the block code for the same latency. Now, you may say, well, a couple tenths of a dB, why is that such a big deal? Well, in many applications it's not a big deal, okay? But when we're talking about these capacity approaching codes, a couple of tenths of a dB is a big performance improvement because they're all so good. I mean, you can only get to capacity, okay? So the block codes that we're comparing to here are excellent codes, okay? So we do get some gain with the spatially coupled versions in the finite length regime. Notice again, though, that if our window size is too small, we actually lose, okay? And generally speaking, with the spatial coupling, we have to choose a lifting factor and a window size, and I said before there's a trade-off. A large lifting factor Again, this is the size of the permutation matrices that we put into the Protograph. Really improves the code performance. It makes it a better code. A large W improves the decoder performance. Okay, because the size of the window relates to how the decoder is going to be able to perform. So too small a W, there's nothing wrong with the code, but the decoder is not doing well. And too small an M, there's nothing wrong with the decoder, it's just that you don't have a strong enough code. But there is this trade-off between these parameters when designing spatially coupled codes in the finite length regime. Now here's so we tried to look at this in a number of different ways. Here we looked at complexity. Okay, and when I say complexity, I just mean number of node updates. So every time you pass a message, it depends on the degree distribution of the code you're using. It depends on the number of iterations you're using, and it depends on if you're doing any kind of fancy decoding schedule. This study included non-binary spatially coupled, both block and spatially coupled LDPC codes, which people have looked at a lot in recent years. And we don't really have to look at all these curves. Let's just look at there's one set. The blue set is for 4600-bit latency. The orange set is for 6900, and the purple set here is for 13,000. We can just look at the blues. So this is the complexity, some kind of normalized complexity per decoded bit of the block codes. This is field size down here. So I think particularly if you're talking about non-binary codes, you'd better worry about complexity. So we can see that the complexity is in all cases getting higher as we increase the field size. But the spatially coupled code complexity is somewhat higher than maybe a factor of 50% higher or something like that than the block code, corresponding block code. Now this is with standard stopping rules. Again, you could make this comparison all kinds of different ways. You could let each of these kind of codes use their best update schedules and stopping rules. When do you stop iterations otherwise? And of course that's going to affect the computational complexity. But this is just without trying to do anything fancy like that. One thing to note about this, even though the spatially coupled code requires some additional node updates, it gets the better performance by a couple tenths of a dB. And one thing to notice is that the block code, you cannot do additional iterations and improve the performance of the block code. Otherwise, this is the performance of the block code we showed is the best you can get. So the spatially coupled code has that gain. It can't be compensated for with a block code of the same latency just by doing more iterations, okay, or by doing more updates. So the performance gain is a real gain, but we do pay a penalty in complexity, computational complexity. Now, this is another way of looking at the same thing. Now we said, let's say we're going to operate at 1.5 dB, a little above the 3/6 regular threshold, and we want a 10 to the minus 5 error probability. And we're going to look at spatially coupled codes and block codes, which both achieve 10 to the minus 5 at 1.5 dB. Okay? And we look at different field sizes. The blues are the block codes, and the reds are the spatially coupled codes. And the ones down at the bottom here, this is computational complexity again. This is still latency. The latency required to achieve this error rate at this signal-to-noise ratio. So we see here that in the binary, if we compare the binary, this is the block and this is the spatially coupled, you can get that performance. I had said previously that the spatially coupled code has that couple tenths of a dB advantage with the block code, and additional computation with the block code can't overcome that. Okay, so what we're doing here is we're stepping that back and let's saying, all right, let's say weaken the spatially coupled code a little bit so its performance goes back to what the block code performance is. And then it with the weaker code, or not necessarily the weaker code, but maybe a smaller window or fewer iterations, it gains back some of that complexity. So what's the net comparison with complexity if you equalize the performance as well? So in the binary regime, we can get the same performance with about half the latency with the spatially coupled code with just a little bit more computational complexity, not the 50% that we had before. With the field of size 4, we again get a big advantage in latency. We get the same performance with about a factor of 3 less latency. Again, with just slightly higher computation complexity, almost equivalent. So when we scale back the performance and say we're going to compare these on the basis of the same performance, on that basis, then the spatially coupled codes have a complexity advantage. Okay, when you try to compare on the basis of the same complexity, block codes would have a complexity advantage if the spatially coupled codes are allowed to perform better. These are the 8-area results here, and this is a 16-area result for spatially coupled codes. Now, a couple of things to notice. With small field sizes, as you increase the field size, like 2 to 4, 2 to 4, and up to 8, the latency decreases. Same performance, so you get the same performance with less latency by going to a higher field size, but of course the decoding complexity does go up. Another thing to notice is that as you go to larger Q, however, notice in this case and here, when we go to the larger field size, either block or spatially coupled, the latency gets higher and the complexity gets higher. So there'd be no reason to do that. I mean, to achieve a particular error rate, you may be willing to use a higher field size to get a lower latency, but you're not going to be willing to use a higher field size to get a worse latency. So, yeah.
Non-binary codes, what kind of decoding algorithm?
This is just belief propagation decoding. It's the same decoding. There's versions of belief propagation that work in over any finite field, basically. So there's, it's the same algorithm. Now, what we can, and again, this is not analytical, so it's not anything that you can draw general conclusions from, because as you can maybe appreciate, there's a lot of different factors that you need to trade off to look at what gives you the best performance here. You've got complexity, you've got latency, you've got performance, you've got field size and other factors, window size and things like this. So lifting factors. But it looks like if you're willing to tolerate some additional complexity, that you are able to gain a little bit in latency if you want to code over GF4. Design either block or spatially coupled codes over GF4. And other people have looked at this from other points of view, and I think that they have come to similar conclusions that 4-area LDPC codes may be of interest, maybe give you good trade-offs. It doesn't seem, at least from what we've looked at here, that going to higher order fields would pay off unless complexity, you just don't care about it. Now, that's kind of one topic. So trying to do a fair comparison in terms of latency, performance, complexity between the spatially coupled and the block codes in the finite length regime. Another thing you can do to get rate compatible codes is you can do puncturing. Otherwise, if you want to, this is often something you want to try to do in standards. In standards, You oftentimes want to be able to operate at different rates depending on the channel conditions. So puncturing is one way you can do that. So we've looked at, you puncture, it just means you don't send certain bits. You generate a code word and you don't send certain bits. But at the decoder, you assume, I mean, the code is designed based on all the bits. So the decoder design assumes that you have all the bits. So what do you do with the bits that aren't received at the decoder? Yeah, you start them out with, you start out the decoder, the LLRs at 0. So you assume that they're equally likely. But you need to, you can't throw them away at the decoder. They're used because they're part of the structure of the code. So if you have a puncturing fraction alpha, then you get a rate R of alpha, which is the rate of the mother code divided by 1 minus alpha. So you get higher rates this way. And again, these are just simulation results just to see how some of these spatially coupled codes hold up with random puncturing of symbols. We didn't try to do any smart puncturing or anything like that. This, again, the notation kind of varies among some of these slides because they're taken from a couple of different talks. But this is just a 3/6 regular ensemble with a termination length of 50. And the alpha equals 0 curve here is no puncturing. So this is erasure channel results. This is no puncturing at all. So this is the simulation for a 3/6 regular code. This is the threshold. With this termination factor, the rate loss is from 0.5 down to 0.49. And this is the corresponding threshold. So we see here, we're fairly close to the threshold. Our lifting factor was 500 and our window size was 8. This was all with window decoding because we want to say what we're getting with a certain latency, 8,000 bits in this case. And in this case, we allowed, each time we're in the window, we do 10 iterations in a window and then we shift. So it's not any, we weren't using any stopping rule or anything like this. We were just iterating a fixed number of times, decoding the target symbols, and then shifting the window. And these are the results for the punctured versions. Now here we did a 1% puncturing here, which gives almost the same result. But here we did 10% puncturing, so we have a higher rate. And these are the straight lines are the related thresholds. Because what we wouldn't want to see is when we do this, if the performance gets further and further away from the threshold. Okay, we feel good about this as if we puncture and our performance is still close, about the same distance from the threshold. And that holds up here all the way up to about 35% puncturing, where we get our rate up to 0.75. So we could say robust decoding performance in the sense that we get performance close to threshold for a variety of rates, from a half up to 3/4 in this case. We have a small gap to threshold in each case. Now you may say, well, that's still a fair gap here. But of course, we're fixing the latency at 8,000. If we want to make this gap really small, we'd use 80,000 or something like that. Okay, so that's not so much an issue. The issue is the relative gap to threshold as we go to the higher rates. And that stays almost the same. Another point that's worth observing is this was done, simulation was done all the way down to 10 to the minus 7, and there are no observable error floors here. Okay, and again, with block codes that are capable of getting really close to capacity, like that have the good thresholds, like the irregulars, at these rates, at these error rates, you would begin to see error floors typically. Okay, we'll actually have a little bit more on that in a second. This is just the same picture for the Gaussian channel. Yeah.
Erasure channel. When we are puncturing a bit, sometimes we not having an erasure.
Yeah. So you're in the erasure channel, you're just starting the decoder with erasures in those symbols. Yeah, yeah, yeah. That's right. Yeah. Actually, we had to, I mean, that is true, and we did there's some analysis that we did on this with erasure channels in terms of being able to predict thresholds of punctured LDPC codes on erasure channels, and it relies on exactly what you just said. Yeah. Sure. I mean, it does affect dmin, and but you know, anytime you go from a lower rate to a higher rate, you're going to have smaller minimum distance. I mean, if you redesign codes, fresh code for each rate, the higher rate codes will have a smaller minimum distance. So the question is, does the puncturing kind of hurt you more than you would expect? I mean, if you think back to the Gilbert-Varshamov bound, the minimum distance growth rate gets smaller as the rate gets higher. So you'd like the minimum distance that you get from puncturing not to decrease it any faster than that. So this, I mean, we don't know. I mean, this is just random puncturing, but it indicates that we're not, the fact that there are no error floors here indicates that they're probably not killing ourselves with regard to distance. So this is really just the same picture for the Gaussian channel. The only thing here is when we got up to rate 0.75, the gap is more of about 1 1/4 dB, whereas down here the gap was only about 1 dB. So I don't know why that is. Again, this is just some experimental work we did to get kind of a sense of what was going on here, but somehow that if we puncture too much on the Gaussian channel, there seems to be a little fall off in what we'd expect. It could just be a result of the particular puncturing pattern we picked or the particular code, we're not sure. But it looks like still the performance is pretty robust of these codes to puncturing. And I said we do have some analytical results on this, on the random puncturing, which show that the thresholds hold up well. Okay. Now what about if we did a comparison? So sometimes you could say, all right, you've got your regular codes and you spatially couple them, and they have this advantage compared to regular block codes. But we know that irregular block codes are at least better in the threshold than regular block codes. So what if you actually just did a comparison of your regular spatially coupled codes to your irregular block codes? Okay, and again, it's difficult to do anything analytical on a problem like this, but you just take something reasonable, what we thought was a reasonable comparison. So we grabbed an irregular repeat accumulate block code out of the WiMAX standard. It's based on a protograph with 24 variable nodes and 12 check nodes. It's a rate of half. We gave it a lifting factor of 250, so a block length of 6,000. And it has rate of half. Its BEC threshold is about 0.45, so it has pretty good thresholds. Gaussian channel 0.82 dB, better than any regular code. Okay. Any regular rate 1/2 block code. So to compare it to, we picked a 3/6 regular spatially coupled code. We picked L equal 50, so we had a little rate loss down to 0.49. Our thresholds here are actually much better because they're from a spatially coupled ensemble. But again, we're not comparing asymptotics here. We want to compare actual finite length performance. So the spatially coupled code, we chose a window size of 6 and a lifting factor of 500. That gave a 6,000 bit latency also. So the latencies were the same and the memory requirements for the decoder were the same. Now, in trying to make a comparison like this and try to do maybe some semblance of fairness, you know, if we're going to do 100 iterations with the block code, if we're using window decoding, okay, we can't do 100 iterations. So when we say we do 100 iterations with a block code, it means every node gets updated 100 times. With the sliding window, if the window size is 6, a particular node will be within the window 6 times because it shifts one set of symbols at a time. So if we do 100 iterations on a particular symbol when it first enters the window, and successive window positions, we'd be doing another 100. So we'd be doing 600 iterations on each symbol. So that wouldn't be fair from a computation standpoint. So what we do is we allow fewer iterations per symbol for the spatially coupled code when it's in a window position, so that to more equalize the total number of iterations between the two codes. Now, we didn't do this exactly, we just approximately. So if we look, here's our IRA, no, this one is our irregular block code with only 10 iterations. And the performance is not particularly good, and we start to see a little error floor. Here is its performance with 100 iterations. Okay, so now we're giving it enough iterations to get the performance we'd expect out of this. But it still shows an error floor down around 10 to the minus 6, because again, this is highly irregular design. This ensemble doesn't have linear distance growth. They're not asymptotically good ensemble, so we expect to get this type of thing. Now, the spatially coupled code allowing 10 iterations per window position, which would really, actually, we should have done this, since our window size is 6, we should have given this guy 60. There should have been somehow a ratio of 6 to 1. Here, actually, we gave the irregular code a little bit of an advantage in terms of iterations. But our spatially coupled code does this. So we lose a little bit in the waterfall region compared to the irregular codes. And remember, that's the whole idea of an irregular code, is that you want to improve performance in the waterfall region, get better thresholds. But the spatially coupled code shows no sign of an error floor, whereas the irregular code is definitely starting to show an error floor. So what we would say with spatially coupled codes, if you want to compare them to a good irregular design of a block code, you may, on an equal latency basis, you may lose a little bit, a couple of tenths of a dB in the waterfall, but you will gain in the error floor, and you have a simpler implementation complexity because you've got the regular structure. So that's kind of that kind of trade-off. Again, or comparison, again, it's just based on some simulation results, which we think are kind of fair, but it's difficult to say, draw general conclusions from this work. But more or less what we're seeing here is that in the finite length regime, these spatially coupled codes are holding up pretty well. They're doing quite well, okay, according to a number of different measures. Now this is just if we do random puncturing now of the irregular repeat accumulate code and the spatially coupled code. And we kind of see, this is what we already showed. We puncture up to rate 2/3, and we have a similar thing. Again, the IRA code starting to show a little error floor. Up here, they're almost, actually, what's happening at the higher rate, the spatially coupled code loss in the waterfall is becoming less. We don't know why that is, but maybe it's just a fluke. We didn't simulate down far enough here. This will probably start to show an error floor pretty soon. You may notice that the blue curves, which are spatially coupled, also are starting to show a little change of slope there. So I don't want to claim that they have no error floor. Okay, they would exhibit no error floor. That would not, and that's something that is still an active research area. Even though these codes have linear minimum distance growth or free distance growth with constraint length, there still may be issues with whether how they handle absorbing sets or trapping sets and things like this down at the very low error rate range. So that's still an active research topic. in designing good spatially coupled codes. Okay, so that's more, I don't know why the IRA code kind of fell apart when we punctured that much, and I don't know why that is. Now, I think this is kind of more or less the last topic. So, with block codes, you can look at the performance in two ways. You can look at block error rate, or you can look at bit error rate. Almost all the performance plots that we've given in these notes are in terms of bit error rate. It's easier to compare block and convolutional codes when you compare bit error rate. And convolutional codes are kind of naturally suited to bit error rate because they don't have a block structure. But of course, when you terminate a spatially coupled or convolutional code, you do have a block structure. And we like to call this a frame error rate simply because there's something else we're going to call the block error rate. The frame error rate depends on L, and actually it's pretty, I guess it should be obvious that as L goes to infinity, you have a fixed protograph here, and as L goes to infinity, the frame error rate's actually going to go to 1. All that means is that if you continue decoding forever and ever, you're eventually going to make an error. It's all one big block, okay? Now the bit error rate is more the error rate per unit time. You can look at this issue of frame error rate, and this is a paper by Olmos and Urbanki. They had developed some methods of looking at the scaling behavior of low-density parity check block codes. Otherwise, how the finite length performance changes as you change, say, the lifting factor, which goes into a protograph, or the block length of the code. Now, they were able to do the same thing for the convolutional or spatially coupled versions in terms of looking at this frame, terminated frame, as a big block. And they get results. They have I can't remember, I think the solid curves, one set of curve simulations, the other set of curves, no, the dotted must be the analysis, and the solid ones must be the simulations because they don't go down as far. Yeah. But you can see that they're pretty good. Otherwise, they use, this is erasure channel analysis. They use this peeling decoder, which is kind of what whoever asked the question earlier about that. And they get a very nice way to estimate how the block error rate varies as a function of block size. And the estimates are quite accurate. So this is a useful tool, again, if you want to design spatially coupled codes to kind of see how your performance will vary with termination length. But if you're using the sliding window decoding, it's not as relevant. Actually, this is something ongoing now with our group that we're working on to try to apply the same kind of analysis to sliding window decoding. In window decoding, you're not decoding across an entire frame, okay, with passing messages across the entire frame. You're just decoding within a window and just estimating one set of target bits at a time. So another kind of measure of performance that we can think of with convolutional or spatially coupled codes, we could talk about a block error rate. That's why I called this frame error rate. I mean, this little protograph, we have 2 variable nodes per time unit, and we have a lifting factor, which is maybe 500 or something. So every time the window shifts in decoding, we're decoding 1,000 bits. So in lots of applications, it would be of interest to what's the probability that each time we decode one of those blocks of 1,000 bits that we have some errors. Instead of just computing the bit error rate, why don't we compute the block error rate? So each time the window shifts, we have another block. So the viewpoint here, this is new. We've always just looked at bit error rate, and people keep asking us about block error rate, and this is the block error rate that makes sense to look at for these codes. So in terms of this little protograph, we have a block size n, which is just the number of variable nodes here, which is 2 times the lifting factor. And then we have, this is a coupling width of 2. Now, here the notation changes again because it came from a different presentation. Instead of using m sub s for syndrome form or memory, we're using little w for coupling width. Okay. Same thing. And that makes the constraint length 6m, same definition of constraint length. The window span, well, we have to pick a window size for our window decoder. And if it's 5, if we pick 5, it's got to be at least one more than the coupling width, okay, to include at least all the symbols that can be connected in one iteration in the window. Usually it's several constraint lengths. This would actually be kind of a short window for this code. So we say it's, in this case, it would be 10 times the lifting factor. The strength of a convolutional code comes from its constraint length. I mean, the distance grows linearly with constraint length. Bigger constraint length, bigger free distance. The latency depends on the window size. So this is the expression for constraint length. This is the expression for latency. We'll use our window size, S. And since the window, the number of blocks in the window has to be at least the coupling width plus 1, the latency must be at least this. So we can view this kind of setup here if we want to think of either the constraint length, the strength of the code, or the latency, the window size, as being fixed. We can design codes like this in different ways. We could use a large blocks by choosing a big value of m, but small coupling widths by choosing a small value of w. Or we could use larger coupling widths, a bigger value of w, and smaller lifting factors m for the same constraint length or the same latency. So again, this is another design issue. How should we design these things? Should we use big lifting factors and really short coupling widths, syndrome former memories, or should we use larger syndrome former memories and smaller lifting factors? Again, these are kind of questions that density evolution asymptotic analysis cannot answer. Okay, because in the asymptotic analysis, all these things have to go to infinity in order to get your results. So you can't compare the different values. So when we talk about varying the coupling width, these are 4 different protographs with different, they're all of the 3/6 variety, but they're all with different coupling widths. Here's one with width only 1, where we still have some double edges. Here's kind of the standard one that we've been working with so far, but we could use larger coupling widths by spreading the edges out over to 3 adjacent time units, or even to 4 adjacent time units, and we could keep going. And actually, if you think of this, you could use extremely large coupling widths and very small lifting factors. To the point, and kind of the limit of that kind of thinking, the lifting factor may be 1, so you'd just be decoding 2 bits at each time unit with your window decoder, and you'd have an extremely large memory or coupling width. Okay, and that's kind of the traditional kind of convolutional code that you think of, is you have a small, in the notation we were using the other day, k and n, k equal 1, n equal 2, say, and a huge memory in the encoder. Okay, that would be the view where we have a lifting factor of 1 and we have a huge coupling width. But another way of looking at it is shortening the coupling width and having bigger lifting factors. And either way we look at it, we can keep the strength of the code the same by fixing the constraint length and keep the latency the same by fixing the window size. So what's better? So again, we've looked at this experimentally. We have, here's this is for fixed constraint length. We're looking at increasing the coupling width from 1 to 4 and decreasing the lifting factor from 1500 down to 600. So the constraint length is fixed at 6,000, and for the window sizes we've chosen, the latency is also fixed at 36,000. And we have block code comparisons here and spatially coupled code comparisons here. And the difference between these two is, again, that kind of convolutional gain, because we're taking the block codes. Well, no, it's not quite the same here. I have to remind myself. Here we're comparing this block size. Okay, otherwise we define this n. So we're going back to this. We're giving results on the error probability of a block. Each time the window shifts, we decode a block of symbols, target symbols. And we're comparing that then to a block code of that size. Now that is kind of essentially the same as this convolutional gain comparison, and that's why you see this big gain. But for a given block size, so we've already noted this, the penalty is we have a larger latency here. The latency of these block codes is only their block length, whereas we've got a much bigger latency here. So this is the same kind of issue. But we're now comparing block error rate with the spatially coupled codes to the block error rate of the block code rather than the bit error rates that we showed earlier. And the comparison is similar. We still show this kind of convolutional gain. Now, how about, let's do the other thing that I mentioned. How about if we fix the coupling width, the code memory, and scale the lifting factor? So our coupling width is 2, and we choose bigger and bigger lifting factors, giving us bigger and bigger blocks to decode, larger constraint lengths, and larger latencies. Well, all of that should help, right? So we get better performance. We get this kind of improvement. But what we're interested in is kind of how much we're gaining as we increase these parameters. How well it scales with the performance scales with these parameters. The next part of this figure we're going to show is, let's fix the m now and vary the w so we get the same parameters and see how the scaling looks like there. Well, if we use the little w equal 1 protograph design, which with the same constraint length as this, we get this performance, not quite as good as the other one that had that constraint length. The second one, if we go to the w equal 2 protograph here, it's actually the same as the second curve here, so there's no difference in that one. The third one, so we go to w equal 3 now, and we have a 6,000 constraint length. We're comparing that with this one, the w equal 2 with a 6,000 constraint length, and we see the performance is better a little bit. And when we go further, w equal 4, which gives us 7,500 constraint length, compared to this edge spreading with 7,500 constraint length, again we gain. So each time we're increasing the w here, we're decreasing, or no, excuse me, we're fixing the lifting factor and increasing the w and getting increased constraint lengths. So what do we say? Well, the one observation which was a little surprising for us, the scaling is better with the coupling with w. Otherwise, these curves, the solid curves, are spread out more than the dotted curves. The dotted curves are more grouped. So again, this is one example. It doesn't tell the whole picture, but it gives us a sense, and this was a little bit of a surprise, that if we want to fix the constraint length, the strength of the code, or the latency of decoding, we can do better maybe by keeping the lifting factor smaller and increasing the coupling width than we can by keeping the coupling width small and increasing the lifting factor. These are very difficult things to analyze. We are working on something for the erasure channel, as I mentioned, where we hope to get some analytical insight into this. But this was a little bit of a surprise to us that the scaling behavior was better with the coupling width than with M. This was just given at the workshop last month in Cambridge. Now, we're out of time, so I'm going to skip I think everybody's tired, including myself, okay? This is also something just out of this most recent talk. As I go through the flipper here, I'll say what we did. We took an outer code, a high rate outer block code, BCH code, which can correct a few errors, and we used that to protect the target bits that we're decoding each time the window shifts. So each time the window shifts, we're decoding a block of target bits. And we can protect those target bits with an outer code. Okay. What do we hope to gain out of that? Well, we hope to gain better performance in the error floor, because just a couple of residual, now we're counting block errors. A couple of residual decoding errors in a block counts as a block error. Okay, so if we want to minimize block errors, we do not want to tolerate decoding a block of target symbols and having just a few residual errors there. So we use an outer code. And this is its performance. Now this is just, again, our first try at looking at this. And we lose in the waterfall, which we expect because we pay a rate penalty with the outer code. Okay, but we do clean up errors. It looks like we're cleaning up errors in the blocks of target symbols by taking this approach. So this may be something, if error floor is an issue, that people would want to look at in terms of trying to avoid any error floor problems that these codes might have. We could also use the outer code as some kind of a stopping rule for iterations also, if we wanted to try to reduce computational complexity. Now, just to wrap up by mentioning some of the implementation aspects of spatially coupled codes. They may be attractive for future coding standards. Here's some of the things that may make them attractive. These permutation matrices can be circulants, which would give us quasi-cyclic designs, which would allow implementation to be simplified. Again, once you do this, you can't guarantee those asymptotic properties anymore. But the expectation would be that if you, starting with a good ensemble and you choose circular liftings, you would still get good codes with high probability. I should be careful about that statement, okay. The expectation is these would be good, okay. The asymptotically regular structure is nice also for hardware implementation. There are systems type advantages with regard to you have flexibility with this termination length. You have flexible rates that you can get by varying the termination length or the lifting factor or puncturing. And then, of course, if you have an application which requires streaming data, is not naturally blocked, these are well suited for those kinds of applications. And I mentioned this, that at least in my opinion, for practical applications of these codes, the outstanding issue which still needs to be looked at is, even though we have linear distance growth, we're still using belief propagation decoding. So there are graphical structures which can cause errors that have nothing to do with minimum distance. So issues like stopping sets, trapping sets, and absorbing sets, how sensitive are these spatially coupled codes to those kind of graphical structures? And again, we have some work going on in that area with some colleagues at other universities. So to summarize, they're spatially coupled LDPC code ensembles. They achieve threshold saturation, which means their iterative decoding thresholds approach the map decoding thresholds of the underlying block code ensembles. This threshold saturation property, along with the minimum distance growth, linear minimum distance growth property of the JK regular versions of the spatially coupled codes, combine the best aspects, at least the asymptotic properties, of the regular and irregular block codes. So with window decoding, these in the finite length regime, these codes can compare favorably to block codes, and you get flexible trade-offs between the performance, the latency, and the complexity, as we showed on several different ways. They can also be punctured to get robustly good performance for a certain range of higher rates. And it looks like using an outer code can be beneficial, particularly if you're interested in measuring the block error rate of these blocks of target bits as they come out of the window decoder. And those of you that are still students, if you are interested in spatially coupled codes, I could highly recommend that you contact Dr. Mitchell, who probably knows more about the details of designing good spatially coupled codes, particularly in the finite length regime, than any of the other researchers working in this area at this time. So be happy to answer questions if there are more questions.
So are there any results about rate adaptation with these codes?
Rate adaptation.
Yeah. I mean, as the SMR varies, sometimes we need to downgrade the modulations.
Well, I mean, this would be a little bit with the puncturing. I mean, you can do that type of thing. Yeah, I mean, maybe you reduce the size of the signal constellation or something like that. I mean, these codes, the research that's gone into these codes has been primarily fundamental research on asymptotic properties. In terms of looking at their performance for practical applications, not so much has been done. There are groups. There's a group in Germany that's looking at them for satellite communication problems, I think. But, you know, this is still fairly new, as I think it is with polar codes too, in terms of looking at how they would work in a real environment and what are some of the practical issues involved in the systems level in terms of employing codes like this. Any other questions? Well, thanks for your attention. You've been a good audience. I've enjoyed the interaction, and if you have any, I'll be around through Thursday if you have any other questions that you forgot to ask me. Or if some of you want to ask more about turbo codes. We had originally planned to put some lectures in on turbo codes, but it turns out there wasn't going to be time to get. I mean, it was titled Modern Coding Theory, right? Or what? Recent advances. So advanced topics. So the spatially coupled, the LDPC and the polar are a little bit more up to date than the turbo codes. But my memory, I used to work in turbo codes 15 years ago. I haven't looked at them recently, but I'd be happy to try to answer questions on those if you have them. Okay, that's it, I think.